Bismillahirrahmanirrahim. Assalamu alaikum, students. In the last lecture, we discussed TDS equations. Today, we will continue. I will try to derive some useful results. I will write some useful results from TDS equations. Right. So first, let me write TDS equations. TDS equal to CV dt plus T times dou P by dou T at constant T. Sorry, it is at constant V. Constant V dV. Let me check it. TDS equals CV dt plus T dou P by dou T volume held constant times dV. This is our first TDS equation. So this is my first TDS equation. The second one is TDS is equal to Cp dt minus T dou V by dou T at constant P dt. TDS equals Cp dt minus T dou V by dou T at constant P dt. So this is our second TDS equation, right? You know the symbols. Cv is heat capacity at constant volume, S is entropy, T is absolute temperature, P is pressure, V is volume, Cp is heat capacity at constant pressure, right? So first, if let me name it result first. If the process will obtain results using these equations, if the process is isothermal a reversible change of pressure, change of pressure. So if the process is isothermal, a reversible change of pressure, so what can we obtain from second equation? Then from second, that means second TDS equation, where the process is isothermal, that means change in temperature is zero. Temperature of the system stays constant, right? So what will happen to this equation? Second, this term will vanish, will become zero. We will get TDS is equal to minus T dou V by dou T at constant P dP, right? TDS equal to minus T dou V by dou T at constant P times dP. And you know what is this TDS for a reversible process? Is dQ, small heat put into the system. So therefore I can write dQ is equal to minus T dou V by dou T constant P dP, right? dQ equal to minus T dou V by dou T at constant P dP. So therefore, if I have to find the total heat put into the system, I can integrate this equation. So let us do it. Therefore, Q net heat put into the system is minus T integral dou V by, sorry, this partial derivative dou V by dou T constant P dP. I have just integrated this equation. T we have taken outside the integral because T is constant, right? Pressure is changing during the process. That is our value of integration. So we have minus T dou V by dou T at constant P dP, right? Now using the definition of volume expansivity, using the definition of volume expansivity, beta, you know, beta is 1 over V dou V by dou T at P. Whereas by definition, fractional ratio of fractional change in volume to change in temperature at constant pressure. So if we use this definition of volume expansivity here, the equation for heat we obtain Q is equal to minus T integral V beta dP. Let me name this equation. Equation 3. This is my equation 3. Q equal to minus T integral V beta dP, which can be integrated when the dependence of V and beta on the pressure is known. Now, in the case of a solid or liquid, let me write, in the case of a solid or liquid, neither V nor beta is very sensitive, is very sensitive to a change in pressure, right? Therefore, we can take V and beta out of the integral, assume them as constant. This equation will become then Q is equal to minus dV beta integral dP pi to pf, right? We have taken volume and expansivity outside the integral, assuming them constant. This can be done for a solid or liquid. Pi is the initial pressure, pf is the final pressure. So after solving that, what we get with Q is equal to minus dV beta pf minus pi. I solved the integral, but remember this is valid for solid or a liquid, not for a gas. It will name this equation. This is our equation 4. Now it can be seen from this result that, so I will write from 4, it can be seen as the pressure is increased isothermally. Remember, we are assuming temperature is constant. As the pressure is increased isothermally, heat will flow out of the system. If beta is positive. Why so? If beta is positive, TV is always positive, and you increase pressure, this PF minus PI is positive, Q will be negative. And remember our sign convention, negative Q means heat is flowing out of the system. So conclusion is, if the pressure is increased isothermally, heat will flow out if beta is positive, right? But that for a substance with a negative beta, with a negative beta, such as water between 0 degree and 4 degrees Celsius. Remember, water has the maximum density at 4 degrees Celsius. So if you increase pressure on water between 0 and 4 degrees Celsius, isothermally, it has negative beta, so Q will be positive. That means absorption of heat will take place. Same is the case with, should write, or a rubber band. What's the conclusion? For a substance with negative beta, such as water between 0 degree and 4 degrees Celsius, or a rubber band, an isothermal increase of pressure, increase of pressure causes an absorption of heat. Right? You need to remember these results. Now let us calculate the work done on the system during the compression. Now the work done, we are increasing the pressure, you are making compression, you are doing work on the system. Therefore, the work done on the system, on the system during the compression, during the compression is given by W is equal to minus integral PD. Remember, negative work is work done on the system. By the convention, we will use it in this thermodynamics. Now, at constant temperature, we can write redo or at constant temperature, we can write W equal minus integral dou v by dou p at t p dt. How? Let me explain it. See here, we multiply by dp, write it first, minus integral p, then you have dp, sorry, you have dv, you multiply by dp and divide by dp, right? You have pdv, you multiply by dp and divide by dp. Then this dv by dp, this thing will become partial derivative if temperature is held constant, because here we are assuming volume is function of pressure and temperature. If temperature is held constant, total derivative volume with respect to pressure will become just partial derivative, right? So we have written this, right? Now using the definition of isothermal compressibility. Remember the definition of compressibility? Compressibility is simply what? The reciprocal of bulk modulus. Bulk modulus is change in pressure, ratio of change in pressure to fractional change in volume. Compressibility is reciprocal of that, and isothermal compressibility is the compressibility during which temperature is assumed to be constant, right? So we call it more precisely isothermal compressibility, because when we compress the things, we want to see the change in volume due to change in pressure. Temperature is held constant. We call it isothermal compressibility. So how we define that? We use the letter K in books. We denote it by kappa, or let me use the kappa. Kappa is some differently written K-like letter. So isothermal compressibility is by definition minus 1 over V times dou V by dou P at constant T, right? Minus 1 over V dou V by dou P at constant T. So we put this as a compressibility, isothermal compressibility in this work expression. So we get W is Pi to Pf, V is kappa isothermal compressibility times P dP. V kappa Pd, right? Pi is the initial pressure and Pf is the final pressure. Now, again, for a solid or a liquid, the isothermal compressibility is fairly insensitive to a change of pressure. So what we can do, therefore, we can take V and kappa outside the integral, which is the color for a solid or liquid. We can take V and kappa outside the integral. What will it become? It will become V kappa integral PdP Pi to Pf. V kappa outside PdP Pi to Pf. So when we integrate it, we'll get, it is an approximation, half. First, let me write the equality. It is half V kappa times Pf square minus Pi square. Let me name this equation. This is my equation 5. Yeah, circle it. This is my equation 5. Previous equation was 4. This is the expression for work for reversible isothermal change of pressure, where we can use it for solid or a liquid. Right? Let's move to next result. Let me write it second. We discussed first process as isothermal reversible change. Second one, if the process is reversible adiabatic change of pressure. So the process is a reversible adiabatic change of pressure. During adiabatic process, entropy remains constant. S is constant, right? So from therefore from equation second, that is equation second is my second TDS equation, this one. What I have to do, I have to put for TDS 0 because entropy is constant, DS is 0. So what will we get? And in this equation, I should say, sometimes we approximate it, we take Ignore initial pressure compared to final pressure. We just approximate it as half V kappa PF square, right? Let us move. So I have to put from TDS 0, what will I get? I will get Cp dt minus T dou V by dou T at constant P dP is equal to 0. We are using second equation. Cp dt minus T dou V by dou T at constant P dP is 0. Or we solve for dt. For dt, what will be dt? Will be T over Cp times dou V by dou T at constant P. We have solved for dt. We take this to this side, negative negative will go, dt will be this thing over Cp, which is T over Cp dou V by dou T at P dP. And it can be written as dV beta or Cp dP. dV beta or Cp dP. What we have done using definition of beta, which we have already discussed. You can check it. Now, in the case of a solid or liquid, an increase of pressure produces only a small temperature change, right? And also Cp hardly changes. Therefore, what we can do to find the total change in temperature during the process, we integrate this and take beta and Cp outside the integral. Let me write it. I write it dV beta over Cp integral dP Pi to Pf. We assume what T is constant because sorry, what we're doing, I said the process is reversible adiabatic change of pressure. So I said if we increase pressure in a solid or a liquid, it produces only a small change in temperature. So we assume T is constant and Cp also changes very insignificantly for a solid or a liquid. So for a solid or a liquid, we can write it a finite change in temperature during some process where we change the state from Pi to Pf. We take dV beta Cp outside the integral. It will just become then dV beta over Cp times Pf minus Pi. This is another useful result. Let me name it equation 6, right? So it's clear from this equation that a reversible adiabatic increase of pressure will produce an increase of temperature in any substance with a positive expansivity beta and a decrease in temperature in a substance with a negative expansivity, right? Let me write it. So from 6, it is clear that a reversible adiabatic adiabatic increase of pressure will produce an increase of temperature in any substance in any substance with a positive beta. Whereas in that case, if beta is positive, we change pressure, increase pressure, this is positive, delta T will be positive. And a decrease in temperature in a substance with a negative beta, whereas in that case delta T will be negative, right? Let us move to our next topic, which we call internal, use this color, internal energy equations. We know in case of a pure substance, if it undergoes an infinitesimal reversible process between two equilibrium states, we can write change in internal energy as Bu is equal to TdS minus PdV. Just written first law of thermodynamics, replacing dq by TdS, right? So we are assuming the substance is pure and it undergoes an infinitesimal reversible process between two equilibrium states. So we can write its change in internal energy du as TdS minus PdV. So dividing by BV, we get du by dV is equal to T ds by dV minus P. In case of this term, dV will cancel out. T ds by dV minus P. Now here we are treating U, S and P as functions of T and V. So if T is held constant, then derivatives become partial derivatives. right? So if T is held constant, then the derivatives become partial partial derivatives, and we can write do u by do v T held constant equal to T do S by do V at T minus P. So we have just converted these derivatives into partial derivatives. Right? Do u by do V at T constant equal to T do S by do V. T held constant minus P. Now using Maxwell's third relation, do S by do V at constant T is equal to do P by do T at constant V, do S by do V at constant T is equal to P by do T at constant V. What we do, we replace this partial derivative by this partial derivative using Maxwell's third equation. So what we get, right, we get do u by do V at constant T is equal to T do P by do T at constant V minus P. Do u by do V at constant T is equal to T do P by do T at constant V minus P. Let me encircle this equation and name it. Here used number 6. So it is my equation 7. And this equation 7 is called first internal energy equation. First internal energy equation, right? To show its usefulness, we give example. Example. For what? For usefulness of equation 7. That's first internal energy equation, right? For an ideal gas, for an ideal gas, P is nRT by V, right? So if you find the partial derivative dou P by dou T at constant V, you get simply nR by V. Dou P by dou T at V is nR by V, and dou U by dou V at constant T is therefore, let me write downstairs, and dou U by dou V at constant T is T nR by V minus P. So nR by T nR by V is P. So it is just P minus P, which is 0. What we have done, we have taken the equation of state for an ideal gas, PV is nRT. Then we found the partial derivative of P with T. We held a constant, which is nR by V. Then we used 7. Dou U by dou V at T is T. We substituted for dou P by dou T at constant V as nR by V. Oh, nRT by V is P is 0. What does that mean? It means U does not depend on V, but is a function of only T in an ideal gas. So we held constant T, so this derivative turned out to be 0. That means U does not depend on V, but is a function of only T in case of an ideal gas, right? So you can see easily we calculated or justified the fact that internal energy of an ideal gas is function of temperature only using this uh, first internal energy equation and the equation of state for an ideal gas. So this equation is useful. I just given one example. It can be used in many situations, right? There's a second internal energy equation. So let us move to that. We'll write here second internal energy equation. Starting with, again, du is equal to TdS minus PdV dividing by dP on both sides to get du by dP minus is equal to T ds by dP minus P dv by dt. du by dp is equal to t ds by dp minus p dv by dp. So we have divided by dp. Now here u, s and v are regarded as functions of t and p. So if t is held constant, t is held constant, then the derivatives become partial derivatives, and we can write dou u by dou p constant t is equal to t dou s by dou p constant t minus p dou v by dou p at constant t. Check it. Dou u by dou p at constant t is t dou s by dou p at constant t minus p times dou v by dou p at constant t. Now, using Maxwell's fourth relation, dou s by dou p at constant t is equal to minus dou v by dou t at constant p, we get dou u by dou p at constant t equal to minus t dou v by dou t constant p minus p dou v by dou p at constant t. Check it first. Let me encircle this equation. Let me use this color. We have replaced here dou s by dou p at constant t by minus dou v by dou t at p, constant p. So my equation is now dou u by dou p at constant t is minus t dou v by dou t at constant p minus p times dou v by dou p at constant t. So let me name this equation. It is equation 8. This or equation 8. This equation 8 is called second internal energy equation. The second internal energy equation. We have some other results to derive. This is all for today. Prepare your exams. Don't waste your time. and don't forget to subscribe my channel. Thank you. God bless you. Assalamu alaikum.